Hey, welcome back. So there's one more thing I want to talk about and one more problem we're facing. So I hope I've convinced you, cool, linear algebra, it'll solve some problems, we can combine them, we can use basis functions, we get to use all the quirks of linear algebra if, asterisk, if we represent all of our transformations as matrices. However, there's a challenge here. It can be tricky to represent all our transformations as matrices, okay? And I'm going to go through them and show you how it works, but it's not obvious. And in fact, we can't do some of them with a standard matrix. If I have an x and a y coordinate and I use a 2x2 matrix, there are certain things I just can't do. So I'm going to introduce another technique called homogeneous coordinates. Homogeneous coordinates is a concept from projective geometry, which means it's really hard. But luckily for us, I'll explain just very briefly what it means in terms of us. We're not going to go deep into it. It's a technique from projective. Did I say perspective? I meant to say projective. And it's used to allow us to do things we couldn't do before. And it's used to simplify our calculations. So all that we do to move from regular Cartesian coordinates, x and y, to homogeneous coordinates is we add another dimension. So we add a new dimension. And we call this one W. Call it W, okay? So it looks kind of like this. So instead of having x and y, we now have x, y, w as our coordinate, okay? Or if I'm moving x, y, z, I add a w. Cool. So this is our 2D case. This is our 3D case. So in 2 dimensions, we move to 3D. In 3 dimensions, we move to 4D. I suppose I should put a small h here besides all of these. Okay, so we have x in homogeneous coordinates, y in homogeneous coordinates. And there's a gotcha here, which is really nice. If w is 1, then it's a standard coordinate. So if w is 1, bam, we're back into standard coordinates. There's no confusion. We know exactly what's going on. So given a coordinate like x equals 5, 2, I probably shouldn't call it x, hey? Let's call it p. Then if we have a point of p, then in homogeneous coordinates, it's 5, 2, 1. That's it. It's that simple. Now to go from homogeneous coordinates to regular coordinates, so given our homogeneous coordinates, I can then use x homogeneous and divide it by the w. Y is the y in the homogeneous coordinates divided by the w, and so on and so forth for every dimension you have. We probably shouldn't, come on. This eraser is a problem. It sure is, okay. Yeah, I don't have, yeah. So all that you do is you divide it by w, and including the w. So it becomes 1, right? So we normalize back to w of 1. And we bring everything back with it. I have an example in a second. But I want to say it this way first. Any scalar multiple of a homogeneous point is the same point. So that is for all vectors v, kv equals v. Okay, if I multiply the whole thing, and this makes sense, right? Because, oh right, to bring back, if I multiply everything by 5, w becomes 5. I divide everything by 5, I'm back. Okay, so this is a really simple idea that seems to confuse people. Let me work through an example. I have a point 4, 5, and 1. And I'm telling you, any multiple of that point is the same point, okay? So I'm going to multiply this by 5. We can do that. That's 20, 25 by 5. What I'm telling you is, because of our W's, these are the exact same point in space on the screen. You can treat them the same. And to go backwards, this is 20 over 5. This is 25 over 5. And this is 5 over 5. 4, 5, 1. It's the same point. It's just in homogeneous space and not in standard space, right? So I'll write that out. You divide by W to return to standard points. Cool. I actually have another example in here. Why not? 16, 24, and 4. This is a two-dimensional homogeneous point. So to bring it back to our standard coordinates, I divide it by the W. Let's divide everything by 4. So then divide by W, which is 4. This gives me 4, 6, and 1. Yay! And then the point itself is 4, 6. So even though it's 16 and 24, it's a homogeneous point. Okay. What happens when W is 0? That tells us about a point at infinity. Which makes sense. We can't come back from infinity. We can't standardize it. We can't divide by it. We can't normalize it. It all adds up. So we can't divide. Luckily, we don't really use this, okay? This is not a problem for you. It's only used in special cases. For example, lights at infinity. Like the sun. Right? There's no distance. It's at infinity. Okay? Oh, where am I? There we go. So, yeah. So that's homogeneous coordinates. So homogeneous coordinates, it's just a trick. It gives us an extra spot in our matrix. It gives us a fourth dimension. And as you see, it might seem a little strange right now, but it'll enable us to solve some problems. So now let's start jumping into our actual transformations. So I want to explain the transformations you're going to be doing. They're all called affine transformations. Not asinine, although it might feel like it from time to time. So affine transformations have a couple of nice properties, and we try to stick to them as much as we can. Most of our transformations are affine. Okay, so here are the properties of an affine transformation. They preserve parallel lines. Okay, if they're parallel before the transformation, they're going to be parallel after the transformation. This includes collinearity, right? This is nice because if you're relying on the cross product and the fact that they're not collinear, you're relying on that, you can do affine transformations and still rely on it. It's not going to degenerate your triangles. It preserves proportions and ratios. Okay. However, they do not. I should probably highlight that. Let's use red. Yeah. They do not preserve length. You can make things bigger or smaller, and they do not preserve the angles. So just the ratios and the collinearity. Now, what's really nice about affine transformations is that they are invertible. You can go backwards, okay? Now, the last thing I want to mention about this is that they are closed under multiplication. Mathematically closed. And all that means is if I multiply affine transformations together, guess what? My result is an affine transformation. So you can still rely on all that stuff. So that's really nice. So I'm going to list out the ones that we're going to use. This is the translation. Translation means move things around. Rotation, right? Scale, resize up or down. Shear, that's where you stretch things sideways, like you like turn into like this. Yeah, you shear them, you kind of deform them in a funny way. And reflect, which is just a mirror image. So these are my common ones, okay? That's what most people use, and these are rare. We don't really use them that much, but you know, they're part of what's going on. Okay. So let's learn our first operation. Let's do scale first. Scale is an easy one. Remember, scale, you basically want to multiply all the points by some scalar value. If I want to double the size, I multiply them all by 2. And it kind of looks like this. I have a point before. This is 1, 1, minus 1, minus 1. Cool. I scale by 1.5 and I get a bigger one. Right? 1.5, 1.5. Just like that. No big deal. Minus 1.5. So I scale it. I scale it up by some factor. Now the key thing, and this is going to keep coming up with these transformations that we do, is it scales around the origin. So if all my points are positive before, it's going to just, they all stay positive. If it's centered on the origin, it's staying centered on the origin. And that kind of throws people for a loop sometimes. So I can actually draw that out. If I have my coordinate system here, I can imagine if I have this shape, it's in positive space here, and this is 0.5, 0.5, and this is 1, 1. If I multiply this by 1.5, everything, it moves and scales, okay? So that 0.5, this becomes 0.75, and that 1 becomes 1.5. So it moves as well because you're scaling everything up, okay? If we need to scale around a different point, we do a translate first. And I'm going to come back to that. You can translate first. Okay, so you move it to the center, you scale, you move it back. So the way that this works with linear algebra is we effectively treat all of our points as vectors. We scale those. So for all, where am I? For all p, our p prime is going to be some scalar times p, right? Some scalar, some scale value s. Now what this does is this gives us what's called uniform scaling. Uniform scaling means x and y get bigger, and this, when people think scale, it's generally what they think, right? I'll do a uniform scaling, x and y and z. They all change at the same amount, but we don't have to do uniform scaling. I could imagine having a p prime is going to be, you could imagine applying scalar x times px, scalar y times py, and you could have half, you know, in x dimensions stay the same and stretch it out only in the y and stretch it out in both. So you could imagine then how s of x scales in x, s of y scales in y. No big deal. It doesn't have to be linear. So this is how scaling works. You just multiply. It's pretty easy. But the question remains is we want this in matrix form. Okay, and this is what it's going to look like. And this is a 2D matrix. And we'll learn 3D later, but they're all pretty straightforward. Okay. So I'm going to have scalar x here, how much I want to scale. Scale y here, like that. Now remember this third dimension here, this is our w, right? These are our w coordinates. So this is homogeneous coordinates. So if I have this matrix and I multiply it by my point at x, point at y, and let's just say w's at 1. We can change that to w, it doesn't really matter. It'll work out the same. Now I just do a matrix multiplication. So you see, remember your matrix multiply rule? So the top one is going to be sx times px times 0y times 0w. Then, wow. Okay, the next one is going to be 0x plus sypy. It's a y. And then 0w, and the bottom one's going to be 0px, 0py, 1 times w, or just 1. And so we end up with the same. Okay, so that's it. So if we want to scale, here's our scale matrix. How cool is that? We can apply that to any vertex, and it'll scale it the way that we want. The last thing I want to mention about scaling is that it's not what we call a rigid body transformation. And I'm not going to really delve into rigid body in this class. So basically, we couldn't do it to a real object. And sometimes that becomes really important. If you want to stick to realistic things, sometimes being rigid body, it's important to know that. But scaling is not, because we could not do it to a rigid real-world object. It's not a balloon, it's a rock. Cool. Whew. All right, so we've gone through homogeneous coordinates, and now I've shown you the very first example of how we can use that. What's really nice is this third dimension, it didn't get in our way. It just stayed there. It didn't bother us. The w stayed as 1. Nothing changed. And in most cases, you'll find the homogeneous coordinates, they do just that, okay? So I'm going to take a break, and we'll come back and we'll learn a few more transformations in homogeneous coordinates.